All right, so we obtained the magnitude plot for this transfer function V out over Vs for the RC circuit. Now we need to obtain the phase plot. And so again, what I did was I went ahead and plugged this function into my calculator, and I just plugged in all these 6 values for different frequencies. And now I'm going to go ahead and plot on the y-axis here the phase angle for those particular frequencies, okay? And so the phase for this particular circuit ranges from 0 degrees down to a value of negative 90 degrees. So that's the reason why I drew the plot this way, because the values for phase actually go negative here. So I can put something like negative 45 here, and then maybe like negative 22 degrees there, and then like negative 67 degrees there. Something to that effect, so that we can kind of capture the behavior of this circuit, the phase response in particular. Okay, so let's take a look at my values that I got on my calculator. I'll plot the phase in red instead of blue. And so at a value of 1 hertz for the frequency, I got a phase of negative 0.36 degrees. So that's right around 0. So that'll be like right here. Okay. And so again, let's think about what a 0 degrees phase shift means, or we're really close to 0. Here we thought about what a voltage, basically a voltage ratio of 1 means. It meant that our output was equal to our magnitude. Well, what does a 0 degrees phase shift means? Well, it means that our 2 signals are also in phase. So if my output is this signal and my input is this signal, basically they have no phase shift between them. They're right on top of each other, and they're the same magnitude. That's kind of what we're looking at 1 hertz in this circuit. We're saying that we have at a roughly 0 degrees phase shift at a value of 1 hertz, and a roughly 1 magnitude at a value of 1 hertz. So our output and our input are basically identical to each other, right? And if I were to move this red signal, let's see if I can just move the red one, that would be some kind of a phase shift, a negative phase shift here. So as I increase or decrease the value of this phase, that is equivalent to me moving this signal out of phase with this blue signal, right? The larger this value goes in the negative direction, the further I'm pushing that phase shift, okay? So just wanted to show what that means, what we're representing here on this plot. And of course, I don't know how this is going to work. I probably can only scale it. Yeah, I can't scale it just in the horizontal direction. But as I change my magnitude over here on the left, right, that would be analogous to this this output waveform basically shrinking, right? It's getting to be smaller in terms of magnitude until it's literally 0, and then there's just no amplitude whatsoever, right? But okay, so back to the phase. We're talking about as I decrease this value, I'm basically increasing the distance between these 2 troughs, or peaks on my waveform, distance between these 2 troughs, which is effectively just increasing the phase shift or the time delay between those 2 signals. Okay, so we looked at 1 hertz. Let's look at 10 hertz. I get negative 3.6 degrees, so still not too far from 0, but it's starting to drop. At 100 hertz, I'm looking at a value of negative 32 degrees, so that'd be like somewhere in between these 2, so maybe like right here. At 300, I'm at negative 62 degrees, so I'd be somewhere down here, right? Negative 62 might be like there somewhere, so maybe even a little lower. Okay. And then at 1,000, I'm at negative 80 degrees, so maybe somewhere here. And then at 10,000, I'm at negative 89, which is basically really close to negative 90. So that would look just like that. And so now if I were to go ahead and plot, I guess I should have done those in black like I did for the other one, but it doesn't really matter. If I were to go ahead and plot this behavior, of course, what I see is something that looks like this. Oops. My hand got stuck. Gonna come from 0, go through these points, and then just basically asymptote at negative 90 degrees. Okay, so again, this is telling me that as I increase the frequency, right, as I increase the frequency of the input signal in this circuit, I am seeing my magnitude of my output voltage drop with respect to my input voltage, right? It's going to drop. And I'm also seeing my phase shift push this output signal out of phase with a negative phase shift or a time delay. Basically, this signal starts to lag the input signal by 90 degrees, okay? And so that's exactly what I'm seeing. As I increase the frequency, I'm seeing that my phase decreases, goes down and asymptotes at a value of negative 90 degrees, and my magnitude obviously asymptotes at a value of 0, it basically drops off. And so this right here is the frequency response that we are after, these two plots. Obviously, this is a little tedious. I had to pick some sort of semi-arbitrary frequencies. I knew which frequencies to pick so that I could get this behavior, right? If I would have picked values 1, 2, 3, 4, and 5, we would have seen nothing interesting at all, right? We would have seen roughly 0 phase, and we would have seen roughly 0 magnitude change whatsoever. I knew that we needed to span a pretty broad range of frequencies from 1 hertz all the way to 10 kilohertz to see this behavior, right? And that's exactly why frequency response plots are important, because it's not that we have to draw all of these points one by one every single time. Instead, we can just obtain this function, and then any value of f that we're interested in, we can throw it in, and it'll tell us the magnitude at that frequency, or the phase at that frequency, right? So this is super important stuff, and we're going to get into an even easier way to draw these plots, which are called Bode plots, which is basically just a different way to represent the same data, okay? And it won't be so continuous. It won't be this big, continuous function where there's any given number of values that these points can take on. It'll be much easier to draw. We're going to draw them to where we basically represent this data in terms of just straight lines that will tell us the exact same information, but we need to do a little bit of mathematical manipulation in order to obtain those plots called Bode plots. We're not getting there yet, so for now, this is fine. I just, if anyone has any questions about this, please ask. I want this to be clear. Hopefully this has been clear so far. And I'm going to go ahead and end this video. And in the next video, I'm going to just continue to sort of talk about frequency response and give another example from some LT Spice simulations that I ran to show just what's happening in these frequency response plots. Pretty much the exact same circuit, but I ran it in LT Spice. Okay, so I'm going to go ahead and end this video, and we'll see you in the next one.